In this recording, we're going to solve the problems that we have on the first worksheet, Worksheet A for our first exam. And let's take problem by problem. So the first problem says that we have the vector AB, which is 2, 1, negative 3. And we're also given the coordinates of the point A, which is 1, 2, 3. And we're being asked to find what the coordinates of the point B are. So this is quite simple because if, let's say, the coordinates of B are, let's say, x, y, z, then we know that AB has coordinates that are the differences between the coordinates of B and the coordinates of A. So these are going to be x minus 1, y minus 2, and z minus 3. So in other words, this and this have to be the same, which means that x minus 1 has to be 2, y minus 2 has to be 1, and z minus 3 has to be negative 3, which means that x is 3, y is 3, and z is 0. So what is the point B? It's the point 3, 3, 0, and that's it. Okay. Let's go to the next problem. In the next problem, we want to determine the kind of angle between the vectors 1, 2, negative 1, and 2, 3, 1. So is it right? Is it obtuse or is it acute? And how do we know that? Well, we need to take the dot product of the two vectors. And the dot product will be 2 plus 6 minus 1. I'm taking the products of the corresponding coordinates, which is 7. And it's greater than 0, which means that the angle is acute. Let's go to number 3. For number 3, we're given 3 points, 3, 2, 1. 1, 2, negative 2. And 1, 1, negative 1. And we're being asked to do different things. Let's do one at a time. So first of all, we want to find the vectors AB and AC. Let's do that. So the vector AB is what? I need to subtract the coordinates of the point A from the coordinates of the point B. So it's always the coordinates of the starting point subtracted from the coordinates of the terminal point. So it's going to be 1 minus 3, that's also known as negative 2, 2 minus 2, that's 0, and negative 2 minus 1, that's negative 3. And how about AC? A very similar thing. This time we subtract the coordinates of the point A from the coordinates of the point C. So we have 1 minus 3, which is negative 2, 1 minus 2, which is negative 1, and negative 1 minus 1, which is negative 2. So what is part B asking for? It asks us to take the cross product of the two vectors, AB cross AC, which is I, J, K, negative 2, 0, negative 3, negative 2, negative 1, negative 2. And so delete the first row, the first column, you will get minus 3. delete the first row in the middle column and take the 2 by 2 determinant that results. So that will give you 4 minus 6, which is minus 2, but it's the middle coordinate, so that is going to be 2. And delete the first row and the third column. And what you're going to get is, oops, sorry about this, is 2. So this is your vector. And part C is asking for the area of the triangle with vertices ABC. Well, we know that the parallelogram has area equal to the magnitude of the cross product. So the triangle will be half of that. So we're looking for half the area of AB cross, I'm sorry, half the magnitude of AB cross AC, which is 1/2 of square root of -3 squared plus 2 squared plus 2 squared, which is 1/2 square root of 17, right? And that's the third problem. Let's go to the fourth problem. And the fourth problem is to determine the vector equation. It's better to say a vector equation because they're different ones. So a vector equation of the line which is perpendicular to the plane with equation z is equal to x plus y plus 3, and contains the point 113. Okay, so in general, when we have a plane, its equation is obtained by using a normal vector to the plane, a perpendicular vector to the plane, and a point x naught, y naught, z naught, which means that we get the equation a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And eventually what happens is the coefficient of x is a, the coefficient of b is y, the coefficient of z is c, which means conversely, when you have a plane and you make sure, first of all, that all the variables are on the same side. So I'm bringing z to the left-hand side and I flip the sides. Then the coefficients of x, y, and z are going to give you a normal vector to the plane. So that will be 1, 1, and -1. Now, you have a line which is perpendicular to the plane, and hence it's going to be parallel to any vector which is normal to the plane, which means that this vector is parallel to the line. It's a direction vector for the line, in other words. And since we also know a point that belongs to the line, we can easily write down the equation. So just write the vectorization of the point 113 plus t times 1, 1, -1. And if you want, you can make this into one vector, but that's it. That's the equation of the line. Let's go now to number 5, where it says that we have a plane with equation x plus y plus 2z is equal to 1. And the straight line, so this is a plane, and then you have a straight line given by r of t parametric equation, vector equation, 1 minus t, 2t, negative 1. And it asks us where, if they intersect. I mean, the relative position of a plane with a line can be the plane containing the line or the line intersecting the plane at one point, or the line and the plane having no points in common. But to find that out, think of it this way. The vector equation gives you point on the line in which sense? You plug in values of t, and that gives you the point. The plane equation works how? You find triples of numbers x, y, z that satisfy it, and such points that have those triples of numbers as their coordinates belong to the plane, and conversely. So if you want to see if there is a point that does both. So for that reason, what you need to do is take the components of the line and plug them into the plane. So you will get 1 minus t for x plus 2t for y plus 2 times negative 1, and that should be equal to 1. So you can see that that was my x, that was my y, that was my z, and I plugged in the components of the line. So this will give me what? Minus t plus 2t, that's t, and then I have 1 minus 2 is negative 1. And that's equal to 1, which means that t is equal to 2. So yes, they intersect when t is equal to 2. And in particular, what is the point of the intersection? You have to plug this into the line, the equation of the line. So that will be negative 1, 4, and negative 1. So the point, if we want to turn it into a point, and that will be our final answer, is negative 1, 4, and negative 1. So that belongs to the plane, and it also belongs to the line. Let's go to problem number 6, which is to find the length of the trajectory of r of t is equal to e to the t, comma, e to the negative t, comma, square root of 2 times t. So length of trajectory from t equals 0 to t equals ln of 5. And we have a special request here that says that we want to simplify that as much as possible. We want to write this in the form AB, where A and B are natural numbers. So what is the trajectory, the length of the trajectory that we're after? It's the integral of the speed. So we really need to compute the integral from 0 to ln of 5 of the magnitude of the velocity. So our main challenge here will be that the speed, meaning the magnitude of the velocity, involves a square root, and square roots and integrals usually do not mix that well. So we will need to try to find the simplification. So we start with the derivative. The derivative is e to the t minus e to the negative t, square root of 2. And we take the magnitude of this, which is e to the t all squared plus negative e to the negative t all squared. Let's do this in detail, plus square root of 2 all squared. And this will be e to the 2t plus e to the negative 2t plus 2. Now, this is going to simplify. This is to remember our identity from our childhood, which is a plus b all squared is equal to a squared plus 2ab plus b squared. So conversely put, if you have the squares of two numbers and their double product, then you get the square of the sum. So here, you really have e to the t all squared, and then the number 2 can be thought of as 2 times e to the t times e to the negative t. Let's all remember that if the exponents are opposite to each other, the numbers that you get are for the same base are reciprocal to each other. And finally, you have e to the negative t all squared. So your a and your b are e to the t and e to the negative t. So that will give you e to the t plus e to the negative t all squared under the radical. And now we have the fortunate situation where the radical and the square cancel each other, and that will give you, I'm sorry about this. So again, we have a little bit of my Zoom decided not to cooperate again. I'm sure it's my problem, but I'm not sure what I'm doing wrong. And then anyhow, we have this very nice simplification. So this becomes e to the t plus e to the negative t. And now you just need to integrate from 0 to ln of 5 e to the t plus e to the negative t dt, which will give you e to the t minus e to the negative t. That's the antiderivative from 0 to ln of 5, which is e to the ln of 5 minus e to the negative ln 5 minus e to the 0 minus e to the negative 0. Well, this is 1, this is also 1, so the whole thing here is 0. And e to the ln of 5, again, by the definition of the logarithm, is 5. E to the negative ln of 5 is 1 over e to the ln of 5, which is 1/5. And if you want to follow what was asked for us and of us and simplify, this will be 25 over 5 minus 1 over 5, that's 24 over 5. Let's now go to problem number 7. We have the function f of xy is equal to x y cubed over x squared plus y to the 6th. And we would like to show using the two-path method. So use the two-path method. The two-path method can be used only for one thing, and that is to show that the limit doesn't exist. So somehow we're told here that the limit does not exist, and we wish to use the two-path method in order to establish that. What do we mean by two-path method? We try to approach the point under question. So here, obviously, the limit we want to consider is the limit as xy tends to 0, 0. That's the only point which is problematic for this function. At every other point, you can actually plug in and find the limit, and the function will be continuous. This is the only sticky point, if you like. And assuming that we have solved problems of this type, this is quite straightforward. Start by approaching the point along the x-axis, which are the points of the form t, 0. So if you do that, you will get what? You will get t times 0 cubed over t squared plus 0 to the 6th, which is 0 over t squared, which is 0, and that approaches 0. And on the other hand, if you take, now you need to try to match somehow the exponents if you want to get something that works fine. So this will be something like t cubed comma t, and this will be t cubed times t cubed over t cubed square times t to the 6th. Again, if you've never seen this before, it looks strange, but hopefully it's not the first time that you see something like this. which is 1/2, and that tends to 1/2. So here I'm proceeding along the x is equal to y cubed, which is a curve that would normally look like this. So somehow I'm taking a path, which is not a linear path, that brings me toward that point. The one limit that we found, the one feedback, if you like, from the one path that we chose was 0, the other is 1/2. They're different, which means there cannot be a unified behavior for this function as we're approaching the point 0, 0, which means that according to the two-path method, the limit doesn't exist. And let's do the last problem. So for the last problem, we have the function f of xy to be equal to x over x plus 2y. And we would like to find f sub x of 3, -1 and f sub y of 3, -1. So what is f sub x, first of all? So it's going to be, according to the quotient rule, 1 times x plus 2y minus x times 1 over x plus 2y squared. And if you plug in the specific point, then you will get 1 times 1 minus 3 times 1 over 1 squared, which is simply minus 2. And f sub y is minus x over x plus 2y all squared. And you need to multiply by 2. And so f sub y of 3, -1 is going to be, on the top, we're going to get minus 6. On the bottom, again, we have 1 squared, which is -6. And that pretty much does it. Okay. Thanks for watching.